Welcome back. In today's lecture, we will be covering thermodynamics calculus. So, not all combination of variable results in a unique specification of the state of the thermodynamic system. This is something which we can understand by considering a simple saturated system. So, let us just consider saturated system. Okay. Now, what I am going to do is I am going to just plot TV diagram. Okay. And this is my saturated vapor liquid region. I am going to consider isobar, which is at certain pressure. Okay. Now, once we specify, let us say this pressure P, then the T sat is fixed at P. Okay. It tells you that within this region is going to be two-phase system, but the possibilities of a liquid vapor system along this line will be infinite. Okay. In other words, there is infinite ways to arrange liquid and vapor in this range, okay, or in this within this saturated two-phase region. Okay. So, for example, here there will be certain amount of vapor which will be much less, okay, and here there will be more amount of the vapor, but fixing temperature and pressure do not quantify the amount of the vapor liquid which are present in a given system. So, that means this information is not sufficient to specify unique information or unique values of the vapor and liquid in the system. So, this implies that temperature and pressure at VLE of a pure fluid does not uniquely specify the relative amount of liquid and vapor. Now, similarly, if you consider binary mixture, then at a given pressure and specific volume or density, the system can be realized in many different ways. Binary mixture, now, in addition to the issue of the uniqueness of the system or thermodynamic state, certain privileged variables, which are a set of variables that are natural for specific properties. So, for a given thermodynamic function, there are certain privileged variables which are nothing but natural variables for thermodynamic function, and thermodynamic function expressed in their natural variable contain more information as opposed to expressed in other sets of variable. Okay. So, this complete information in natural variables. Okay. Then in some other sets of variables. Now, in order to understand this, so let us just consider simple first law and second law we will combine it. Let us consider a simple set of equations here. So, if you consider for the closed system, so if we combined statement of first and second law for closed system. Okay. So, we are going to consider equilibrium condition. So, in that case you have nothing but du as TdS minus PdV. Okay. So, if you look at this equation, it is very clear that S and V is natural variable for function u, or that is good enough to express this changes in u. So, this implies S and V are good or natural variable for describing u for a closed system. Okay. Now, formally I can write u as function of u S and V. This implies the derivative differentiation of u as can be written as del u by del S as a function of ds plus del u by del V to constant as a function and multiplied by dV. Okay. Now, if you compare this equation with our first law equation, then you can relate this partial derivatives, okay, in terms of intensive variables. T is nothing but du by ds as constant V. Similarly, if you compare P here, P is nothing but minus of del u by del V at constant S. Now, it is very clear that this particular expression do not capture how much, for example, liquid and vapor amount will be present in a given system for a saturated system. So, we need to provide little more information, that is to obtain the full expression for u as a function also of the amount of material in a system. In addition to entropy and volume, we need to augment this equation. Okay, we need to augment this equation in order to have another set of variables which represent the amount of material present or which affects the u. Okay. So, in order to augment this equation, let me define a variable. So, for this purpose we define an additional partial derivative and so this is again for one component. For one component we defined del u by del n, where n is number of moles at constant SV, and this is nothing but chemical potential of a component. Okay. Now, this is an intensive variable. It has a unit of specific energy such as joules per mole. Now, this chemical potential, which represent the changes in the internal energy with the change in the amount of the material present for a pure system, in order to understand physical meaning of it, we have to take certain example, but it is more or less is quite obscure. But let us take some example. For example, pH meter. So what does pH meter do? It actually measures nothing but chemical potential, okay, not the concentration, this chemical potential. Now similarly, you can also consider examples of diffusion and evaporation. Now what are the this particular phenomena are driven by? Is it by concentration or is it by chemical potential? Okay. So without deriving these concepts, I am just making the statement that this is basically driven by chemical potential difference. Okay. Now we can take an example which possibly you can relate, particularly here in India on a hot and humid summer day. Okay, many times you feel that sweating does not cool you down. Okay, you are sweating but it's not cooling you down, and the reason behind is that there is no chemical potential difference to drive the evaporation of the water on the skin, okay, to the air. So on a hot and humid summer day, many times you see sweating does not cool you down, okay, because there is no chemical potential difference, okay, to drive evaporation. Now this is despite the fact that there is a large concentration difference for water between the wet skin and air, okay. And thus it is not just concentration difference which is responsible for evaporation, but it is basically a chemical potential difference, okay, and thus chemical potential plays a significant role, a fundamental role in thermodynamic, such as similar to temperature and pressure, okay. So let me now complete the differential relation of U. Now for complete information you have SV as well as N. So the differential relation is TdS minus PdV plus mu dN, okay. Now this is for pure system, okay, pure fluid. More generally for multi-component system, you need n plus 2. So if there are n component, you need n plus 2 variables to characterize the state, of the system. In that case, your expression, the fundamental equation, can be written as du is equal to TdS minus PdV plus summation mu I dN I is equal to 1 to a number of components, okay. So this is your expression. Now this equation where mu I is nothing but the partial derivative of u with respect to Ni at constant Sv and Nj not equal to I, okay. Now this particular equation, which is a fundamental equation, plays a significant role in thermodynamics. It is a link, it links key quantities of the first and second law, provide starting point for understanding equilibrium and stability, and it's also it provides a starting point for deriving thermodynamic relation. One should note here that SV and N, these are extensive quantities, whereas T, P and mu, which are conjugate variables of these extensive properties, are which are also the first derivatives of this extensive properties, are intensive variables. Okay. So, we can also rearrange this in order to get an equivalent representation of entropy as a function of u, v, n, okay, for n number of component, and we can rearrange this expression here in this form. Okay, so this is what we have derived. Okay. So, I will stop here and we will continue in the next lecture, multivariable calculus. Okay.